Hello dear friends, in the last video we have already solved a problem on
Butterworth filters.
In this video we are solving another problem on Butterworth low pass filter. The given question is a Butterworth low pass filter with following specifications are given below. The Kp value is given as minus 1.5 dB at omega p is equal to 10 radian per second. Ks is greater than 30 dB at omega s is 30 radian per second. We know that we have to first find the value of n, that is the order of the filter. N is equal to log of 10 raised to minus kp by 10 minus 1 is divided by 10 raised to minus ks by 10 minus 1 divided by 2 log omega p by omega s. Let us substitute the values of kp, ks, omega p and omega s in the formula. Log of 10 raised to 0.15 log of 10 raised to 0.5 minus 1 divided by 10 raised to 10 cube minus 1, we get the answer as minus 3.384, and denominator 2 log 10 by 30 2 log 10 by 30 is minus 0.954, for which we get the n value as 3.54629. Rounding off it to next integer, we get the value of n as 4. We obtained the value of n as 4 from the Butterworth polynomial table. For s is equal to 4, the Butterworth polynomial is s square plus 0.7654 s plus 1 into s square plus 1.8478 s plus 1. Stop. After applying polynomial multiplication and opening the brackets, we get this as the answer, and our final answer is h4 of s is equal to 1 divided by s raised to 4 plus 2.613 s cube plus 3.4118 s square plus 2.6107 s plus 1. Based on this transfer function, we have to find the cutoff frequency omega c. Omega c formula is omega p divided by 10 raised to minus kp by 10 minus 1 whole power 1 by 2n. Substituting the values of omega p, kp and n, we get the cutoff frequency as omega p value is 10 divided by 10 raised to minus kp by 10 is kp is 1.5, kp by 10 will be 0.15 minus 1 whole power 1 by 2n, n is 4, 2 into 4 is 8, whole power 1 by 8. This is the denominator and numerical both are substituted. We get omega c as 11.17. We obtain the cutoff frequency omega c as 11.17 radian per second. We are asked to design a low pass filter, hence we have to apply low pass to low pass transformation. We know that to apply low pass to low pass transformation, we have to substitute s as s divided by omega c, where omega c is 11.17. Substituting s divided by 11.17 in place of s in the above equation, we get this as follows. After opening the brackets and doing appropriate mathematical operations, we obtain the transfer function as 1 divided by 6.42 into 10 power minus 5 divided by s raised to 4 plus 29.2029 s cube plus 426.806 s square plus 3640.340 s plus 15,576.3239 at omega p. Therefore, substituting j omega and in place of s, we know that omega p is 10 radian per second. Substitute 10j in place of s. We get 10j whole power 4 plus 29.2029 10j cube plus 426.806 10j square plus 3640.340 into 10j. We have to open this bracket to solve the power. We know that j power 4 can be written as j square into j square, which becomes 1. Similarly here j cube is there, j square into j, which becomes minus j, and j square becomes minus 1. This j remains as it is. So we obtain a real part and an imaginary part. By summing up the real part, we get minus 17104.2761, and the real part is 7200j. We are evaluating this transfer function at 20 log h of j omega. To find the magnitude under root a square plus b square, by applying this formula we get 20 log 0.83935, for which 20 log 0.83935 is minus 1.52 dB. Another numerical on Butterworth filter, which is of high pass filter. The given question is design analog Butterworth high pass filter that meets following specification. Maximum passband attenuation is 2 dB, passband edge frequency 200 radian per second, minimum stopband attenuation at 20 dB with stopband edge frequency 100 radian per second. For high pass filter, we can see the diagram here. This is omega s dash and this is omega u. For high pass filter, we have to apply backward design equation. Omega s is equal to omega u divided by omega s dash. Omega u is 200 and omega s dash is 100 radian per second, for which we get omega s as 2 radian per second. Low pass normalized Butterworth filter is which has omega p is equal to 1 radian per second. The filter which has omega p is equal to 1 radian per second is called low pass normalized filter. We know that Kp is given as minus 2 dB, omega s is 1 radian per second, Ks is minus 20 dB. Substituting this for these given values to find the value of n is equal to log of 10 raised to minus Kp by 10 minus 1 divided by 10 raised to minus Ks by 10 minus 1 whole divided by 2 log omega p by omega s. Substituting these values in the formula, we get n as 3.701. We have to round off this n value to the next integer. We get n as 4. From the Butterworth polynomial table, we know that the Butterworth polynomial for order 4 is s square plus 0.7653 s plus 1 into s square plus 1.8477 s plus 1. The obtained transfer function is h4 of s is equal to 1 divided by s square plus 0.765 s plus 1 into s square plus 1.8477 s plus 1. By applying matrix multiplication method for polynomial, we obtain the polynomial as s raised to 4 plus 2.6130 s cube plus 3.414 s square plus 2.6130 s plus 1. Now we have to calculate the cutoff frequency. We know the formula omega c is equal to omega p divided by 10 raised to minus Kp by 10 minus 1 whole raised to 1 by 2n. Substituting the values of omega p and Kp and n in the formula, we obtain omega c is equal to 1.0693 radian per second. Stop now. The obtained transfer function is related to low pass filter. This low pass filter we have to convert it into low pass prototype, for which we divide s by omega c. Omega c is 1.0693. To convert this low pass prototype into low pass filter, we substitute 200 divided by s, which is omega u divided by s. 200 divided by s is 1.0693 s, this is omega c, and finally we get 187.031 divided by s. We have to substitute this s value in place of s in the transfer function. By substituting this in appropriate s places, we get the value as 1 divided by 12236422024 plus 17095436.63 s plus 119423 s square plus 4888 s cube plus s raised to 4 whole divided by s raised to 4, where s raised to 4 is the LCM. Sending this to the numerator, we have obtained the transfer function h4 of s is equal to s raised to 4 divided by s raised to 4 plus 488 s cube plus 119423 s square plus 17095436.63 s plus 12236422024. This is the constant term b0 we have obtained. h4 of s at j omega is, we are doing this since we have to evaluate the transfer function at j omega, where omega is 100 radian per second. Substituting 100j in place of s, we get 10 raised to 8 divided by 129412022024 plus 6615436000j, where this is the real part and this is the imaginary part. To find the magnitude, we apply the formula a plus jb is equal to under root a square plus b square. 20 log 10 raised to 8 divided by under root 1294122024 square plus 6615436000 square. We get the answer as 20 log 0.148347, for which the magnitude is minus 16.84 dB.